Well, welcome to Lecture 1. In this lecture, and probably also in the next lecture, perhaps even the next two lectures, we will review some of the ideas that we'll need in this course from linear algebra. This is not going to be a very rigorous presentation. If you want more information, the book lists some good textbooks in linear algebra. All I'm going to try to do here is to give you some of the basic ideas that we'll be needing at the beginning of this course, and it's possible as we proceed that we'll be needing some more in the future. The first idea I want to talk about is a vector space. Now, a vector space, all of us have some idea of what vectors are, and in fact, as we proceed in this course, we'll develop some more ideas about that. Vectors can be a lot more general than what you've all probably studied before. But for now, we can think of vectors as being just arrows, as you have in the past, arrows that have a direction and a magnitude, and we'll consider all the vectors that we study to be based at the origin. So a vector space is just a collection of vectors that satisfies certain mathematical properties. And if you want to know exactly what those properties are, as I mentioned before, you can look in a linear algebra book, or you can look at Wikipedia. I mean, some of the ideas are that you can add vectors together, you can multiply vectors by a scalar and get another vector, and there are there are several properties that a vector space must have along those lines. And if you want the details of that, then, as I said, look at a textbook or look at Wikipedia. But what we're going to assume in this course is that we have some vector space that we're working with, and we're going to be considering what's called a subspace of this. So let me just say here, see textbooks for exact properties, and that's only if you're interested. It's really not very important for you to be able to list all of the properties of a vector space. That's not too important, but it is important that you know about a subspace. So a subspace is a collection of vectors from some vector space and this collection must satisfy the following two properties. One, okay, let me give some names. Okay, let's say that our vector space we'll call it V, and our subspace we'll call X. Okay? And now our conditions on X are as follows. The first condition is referred to as closure under vector addition. And it goes like this. If V1 and V2 are any two vectors in X, then v1 plus v2 must also be a vector in X. And so that's why we call it closure under vector addition. By taking any two vectors in X and adding them together, we can't somehow jump outside of X. We will still end up with a result that is in X. And the second property that X must satisfy, so let me make sure this is clear. I'll say in order to be a subspace, X must satisfy these two properties. Okay? And the second property is called closure under scalar multiplication. And you can perhaps, even having seen property number one, you might be able to guess the way this one will go. If v1 is any vector in X and lambda is any scalar, and by scalar I mean a number, and sometimes we're dealing with only real scalars, and sometimes we'll be dealing with complex scalars. In most of the problems in this course, we will be in fact having complex scalars, but still it's just a number, just a complex number. But if so, getting back to our property here now, if v1 is any vector in X and lambda is any scalar, then lambda v1 must be in X. And so those are the two properties that X must satisfy in order to be a subspace of V. So now, I know all of this might seem a little abstract, but let's look at an example, and I think we'll all agree that it's quite simple. So, an example. Okay. Let's look at something very simple here. We'll let V be equal to R3. This is the set of all vectors with three real components, and I'll just tell you that that is a vector space. If you looked up those properties that a vector space must have, if you go up here, and look at the textbook for the exact properties and check them, you would see that R3 is indeed a vector space. So for the sake of this example, I'm going to let V be equal to R3. And now I'm going to consider a particular X, and we will decide whether or not this is a vector space. So I'll say this. I'll say suppose X is equal to all vectors in V that have Z component equal to 1. Okay? So, for instance, um, 2, 1, 0, that vector is not in X. Now, if you're not familiar with this notation I've just used, it's very simple. Let me explain it. This symbol right here means is an element of. And so this symbol, when you use the same symbol but put a line through it, that means is not an element of. So coming back up here to our example where I say that 210 is not an element of X, I'm understanding the first component to be the X component of the vector. So the X component of this vector is 2. Let's see here. Okay. Here, the X component of the vector is 2. The Y component of the vector is 1. And the Z component of the vector is 0. But remember that X is the set of all vectors in V, that is R3, all vectors in R3 that have Z component equal to 1. Well, here the Z component is equal to 0, so this vector is not in X. Okay? But I'll say, however, 2, 1, 1 is an element of X. And of course, there's an infinite number of vectors in X. 3, 1, 1, 4, 2, 1, 5, 6, 1, negative 3, pi 1, e pi 1. The first two entries can be any real numbers you want. That is, the X and Y components can be any real numbers you wish. The only restriction is that the Z component must be equal to 1. So that's this infinite number of vectors in X, and we now want to ask, is X a subspace of V? And before we do that, I'll point out one more thing. If you think about it for a moment, it's easy to visualize X. V is all of R3, and X, if we looked at all the vectors in R3 that have a Z component equal to 1, that means all these vectors, remember, we're considering all the vectors to have their base at the origin. And so since the Z component of all the vectors is equal to 1, that means the tip of all of these vectors would be on the plane Z equals 1. So in other words, now mind you, it's not necessary for you to visualize things like this. You could answer the question without the visualization, but I think it's sort of nice. If we think of this as being V, here all of space is V, then I'm probably not going to draw this too well. Here at Z equals 1, the plane coming through here the plane intersecting, the plane that is parallel to the XY plane and intersects the Z axis at Z equals 1, that would be the plane that we're talking about with X, okay? In other words, we're thinking about all the vectors that are based at the origin, and they would have tips. Their tip would come right to this plane. And if we put all those, if we considered all those vectors and all their tips, we would get this plane Z equals 1. So that's a way of visualizing X. But again, I want to emphasize this is not really necessary to visualize X to answer this question. You just look at the two properties. Consider the two properties that a subspace must satisfy. Okay, so here are your two properties right here. And I encourage you to stop this video for just a moment and ask yourself this question: is X a subspace or not? and then when you think you have the answer, come back, and we'll do it all together. So please, like I say, I encourage you to stop the video now. Okay, so I hope that after looking at this problem, you came up with an answer of no, this is not a vector space, a subspace. And so let's ask, why is X not a subspace? And the answer is that it doesn't satisfy either one of the properties. And let's see why not. So property 1, closure under vector addition. Well, all we have to do, to this is a counterexample here. We're not trying to prove that X is a subspace. If we were trying to prove that X is a subspace, then we really need to prove that if you pick any two vectors in X, add them together, you'll get a vector in X. So we really need to be general. But when we're disproving it, all we need is one counterexample. So let's go with the vector we've already identified, 2, 1, 1. That's a vector in X. And 3, 1, 1, that's, of course, another vector in X. But 2, 1, 1 plus 3, 1, 1 is equal to 5, 2, 2. And that vector is not an X. How do we know it's not an X? Because its Z component down here is equal to 2 instead of 1. So what we've done here is that we have added two vectors, both of which are in X, but when we add them together, we get a vector that's not in X. So X then is not closed under vector addition therefore it is not a subspace. We really don't even need to check property 2. I will check property 2 just to show you how it goes, but we really don't need to, because as soon as we see that a certain set that we're looking at, if it violates either one of the properties, either property 1 or property 2, then it certainly is not a subspace. But let's go ahead now and look at property 2. Closure under scalar multiplication. Okay, so I will again start off by picking a vector, and I might as well just keep with the one we've been talking about. 2, 1, 1 is a vector in X, and let's just say maybe 3 is a scalar. But 3 times 2, 1, 1 is equal to 6, 3, 3, which is not in X because Z is equal to 3 instead of 1. So X is not closed under scalar multiplication. And as I said, we really didn't even need to check that because we already know that X is not a subspace, but now we're doubly sure. So that's our first example of checking a collection of vectors and to see if it's a subspace or not. Now, let's look at example 2. And let me ask, I'll start off example 2 with a sort of vague question. How could we easily change the definition of X to make it a subspace? I have in mind an extremely simple change that we could make in the definition of X. Remember, the definition of X, let's just review real quickly. The definition of X, if we come up here to where we defined X, is the set of all vectors in V, which is R3. It's the set of all vectors in R3 that have Z component equal to 1. Can you modify that definition? Just make a very small change in that definition and come up with a new set that is a subspace of V. I encourage you to stop the video, think about that for a moment, and try to come up with an answer, and then we'll look at it together. So please stop the video now. Okay. So the answer that I hope you thought of is the following. We're still going to have V equal to R3, but the small change that we will make in X is this. We will let X be the set of all vectors in V such that the Z component of the vector is equal to, not to 1 as before, but to 0. And I claim that that one small change will now give us a subspace. So how do we verify this? How do we verify this? How do we verify that this is a subspace? We must show that X satisfies the two properties for a subspace. So I hope again now that you will stop the video and try to do this for yourselves, and then come back and we can look at it all together. Okay, so I hope that now you have given some effort to trying to prove that X is a subspace, and now we'll do it all together. Now remember, in the previous example we were trying to disprove that X, that was of course a different X, we were trying to disprove that it was a subspace. And so all we had to do was find one instance in which it broke either one of the properties, and that was enough. But now that we're trying to prove that this particular X is a subspace, we really need to try to prove, we need to be general in what we say, and try to prove that it would be, it would satisfy properties 1 and 2 under all circumstances. So let's try to be general in what we do here. Okay? Now remember, property 1 is the property of closure under vector addition. I want to try to prove that this new X, which is the set of all vectors in R3 with z component equal to 0, I want to try to prove that it is closed under vector addition. So the way I will proceed is this. I'll say let V1 instead of picking particular numbers now, I want to keep this general. I want to say x1, y1, and now for the third component of v1, I know that if v1 is going to be in x, the third component must be 0. So I'll let v1 be equal to x1, y1, 0, and v2 is equal to x2, y2, 0. Now, certainly, v1 is an element of x, and v2 is an element of x. That's definitely true because both of these are vectors in R3, and both of them have z component equal to 0. And so now we ask, is v1 plus v2 an element of x? Well, v1 plus v2 would be equal to x1, y1, 0 plus x2, y2, 0, and that is equal to x1 plus x2, y1 plus y2, 0. And notice that the z component is indeed equal to 0, and so this vector is indeed in x. So we see that by picking two completely arbitrary vectors in x and adding them together, we have obtained another vector in x. And therefore, x is indeed closed under vector addition. So property 1 is satisfied, but that's not enough. Remember, for x to be a vector space, we must have both properties satisfied. So now let's check property 2. And, some of you, especially those who have a little bit more experience, can probably already see very quickly that property 2 is indeed going to be satisfied. But let's just work through it to make sure. So closure under scalar multiplication. Okay, and the way this will go, we'll again let v1 equal x1, y1, 0, and lambda be any scalar. Okay, then v1 is clearly an element of x because its z component is equal to 0. And now lambda times v1 will be equal to lambda times x1, y1, 0, which will be lambda x1 lambda x, lambda y1 lambda times 0, but of course lambda, anything times 0 is 0, and so lambda times v1 is equal to the vector whose first component is lambda x1, whose second component is lambda y1, and whose z component is 0. And since the z component is 0, then this is indeed in X. And so we see that by picking a completely arbitrary vector in X, and by picking an arbitrary scalar lambda, when we multiply them together, then we still get a vector in X. And therefore, X is closed under scalar multiplication. And finally, then we conclude, since X satisfies both properties, it is indeed a subspace. Okay, another example very quickly. Let's see, I guess that this would be example 3. And by the way, before I get into this example, let me emphasize that I realize that for some of you, probably this all seems quite abstract, and for some of you, I'm sure this seems like something you've done many times before. But if it seems abstract to you, please don't get discouraged, because this is not representative of the way the entire course will be. It is important that you understand some linear algebra, and I'm trying to convey this in the simplest way possible. On the other hand, for those of you who've seen all of this many times before, please do be patient, because some people in the course have not had any linear algebra course at all, and so especially not in a more abstract way, and so we want to get this down, all of these ideas fixed in our heads, so that we all will understand the course and have a good time with it. So I'd like to give you another example now. Let's suppose in this case V is equal to R2, and so these are vectors that just have two real components, and I'm going to let X equal the set of all vectors it's the set of all vectors in V, and I'm going to call the first component X and the second component Y, just as we have been throughout this lecture. And it'll be the set of all vectors in V such that if you take that first component and add it to the second component, the sum is 1. Okay? And to make sure that you understand what I mean, the vector 1, 0 is in X, and the vector 0, 1 is in X, and 2, -1 is in x, and so on. As long as the x component plus the y component is equal to 1, then the vector is in x. But on the other hand, the vector 1, 1 is not in x because 1 plus 1 is equal to 2. So that's the x that we want to consider in this case. And now I'm going to stop and ask you, and I really strongly encourage you to stop the video and try to do this for yourselves, but figure out now, is X a subspace of V or not? So please give that a try. Okay. And by the way, I intend to say this in our class meeting, but if I forget, I will give you a hint. I've been told by other students who've suffered through my videos that I go very, very slowly. And so if I'm going too slowly for you, if you will look, apparently on YouTube, there is a way, an option you can choose to run the video at a higher speed. And I think that you can run it even as high as double speed. And some students have told me in the past that at double speed it's just about right. So if I'm going too quickly for you, you might investigate that option, because apparently it has really made some students enjoy the lectures a good bit more. Okay. So again, I hope that you have now tried this example for yourselves, and I hope you have concluded that X is not a subspace, and I'll show you how that might be done right now. And then, as before, as in example 1, it's easy. If something is not a subspace, it's usually pretty easy to prove that, because all you have to do is to find one counterexample. And so let me proceed as follows. I'll say, for instance, 1, 0 is an element of X, and 0, 1 is an element of X, but 1, 0 plus 0, 1 is equal to 1, 1, and that's not an element of X. Now, let's make sure we understand everything that's being said here. 1, 0 is an element of X because 1 plus 0 is 1. 0, 1 is an element of X because 0 plus 1 is 1. Now we take these two vectors, 1, 0 and 0, 1, and we add them together, and we get the vector 1, 1. But we know that 1, 1 is not an X because 1 plus 1, when we add the X and Y components, we get 2. But remember, X is a set of all vectors in V such that when you add the two components, you get 1. So this vector, which is the sum of these two vectors that are in X, the sum is not in X. And therefore, X, so we'll say, so X is not closed under vector addition. So X is not a subspace. And as before, it's not really necessary to check for closure under scalar multiplication. But we will. I want to make sure you understand that. Since X has already violated property 1, it is not closed under vector addition. That's it. It definitely cannot be a subspace, because to be a subspace, it has to satisfy both property 1 and property 2. So we don't really need to go any further, but just for a practice, we will. So now we'll check for closure under scalar multiplication, and we can do this very easily. Okay, 1, 0 is an element of X, and 5 is a scalar, but 5 times 1, 0 is equal to 5, 0, and 5, 0 is not an element of X, because if we add the X component and the Y component of that vector, 5 plus 0 is 5, not 1, and therefore that's not a vector in X. So X is not closed under scalar multiplication, and so X is not a vector space, a subspace. By the way, a subspace is a vector space. Okay. I'm just throwing that out there. I'm not, again, I don't, if you're interested in reviewing all the properties of a vector space, you can. I'm just going to tell you that if we have determined that X is a subspace of a vector space, then X is itself a vector space. Okay? And so now example 4, I imagine you can easily anticipate what we would do here. I'll say V equals R2 again, and this time X is the set of all vectors in V such that X plus Y is equal to 0. So just as we did in going from example 1 to example 2, we made just a very small change. Same thing here in going from example 3 to example 4. We'll make this very small change, and instead of X plus Y is equal to 1, we have X plus Y is equal to 0. And I'll ask, is this X a subspace? And you should turn off the video and try to answer this question for yourselves, and then we'll come back. Okay, I hope that you have concluded that this this collection of vectors in V is indeed a subspace, and let's see how we would go about verifying it. And as before, remember now, when we're trying to verify that something is a subspace, we need to try to be general. Okay, so we'll proceed as follows. I'm not going to write out every single detail now, because we've done this enough. We're going to first check property 1, which is closure under vector addition. So I'll pick x1, y1 to be an element of X, and x2, y2 to be an element of X. And then I ask, is x1, y1 plus x2, y2 an element of X? That's the question. Well, x1, we can proceed like this. x1, y1 plus x2, y2 is equal to the vector whose first component is x1 plus x2 and whose second component is y1 plus y2. And we want to know, is this in X? That's why I'm going to put a question mark there. But because we don't know that it's in X, we're asking, is that in X? Well, remember that the way you determine whether or not something is in X is to add its first component and its second component and see if you get 0. So this question that we have there is the same as saying, is x1 plus x2, that's the first component of the vector, plus y1 plus y2 equal to 0? If so, then the answer to this question is yes. If not, then the answer to this question is no. Okay, now you might think at the moment that this is sort of a hopeless question to answer because we don't know what x1 and x2 and y1 and y2 are. But I'm going to proceed in the following way. These are just x1, x2, y1, y2, these are just numbers. So I can regroup this, rearrange the order, like this. Now, I hope that you'll look at this for a moment and agree that this second question is just equivalent to the first question. All I've done is rearrange the order of the numbers. And so we want to know, is x1 plus y1 plus x2 plus y2 equal to 0? Well, let's come over here to the right. We are told here that x1, the vector x1, y1 is in X. Now, what does that tell us? That tells us that x1 plus y1 must be 0. Likewise, the vector x2, y2 is in X. What does that tell us? That tells us x2 plus y2 must be 0. And now, if we use that information down here, then we see that this question right here is equivalent to the question, is 0 plus 0 equal to 0? And of course, the answer is yes. So, that means the answer up here is yes. And therefore, X is indeed closed under vector addition. And now we go to scalar multiplication. Okay, we'll pick, again, x1, y1 to be some vector in X, and lambda is some scalar. And so we'll ask now, is lambda times x1, y1 in X? Well, that's the same as asking, is lambda x1 lambda y1 in X? And that's the same as asking, remember, to be in X, the first component plus the second component must be 0. So that's the same as asking, is lambda x1 plus lambda y1 equal to 0? And now, since lambda x1 and lambda y1 are just numbers, this is the same as saying, is lambda times x1 plus y1 equal to 0? And now we come back over here. And remember, though, that x1, y1, that vector is in X. And what does that mean? That means that x1 plus y1 is equal to 0. And if we now incorporate that information down here, then we see that our question becomes, is lambda times 0 equal to 0? And of course, any number times 0 is in fact 0. So this is 0 equal to 0? And of course, the answer is yes. And so the answer to this is yes. And so x is also closed under scalar multiplication. And since x is closed under vector addition and closed under scalar multiplication, we conclude, so x is indeed a subspace. And there we have it. Okay, so now let's look at problems for this lecture, for lecture 1. And all of the problems that I'll give you, we will take V to be R3 and the set of scalars to be all real numbers. And the instructions for the problems are very simple. I just ask you for each problem indicate whether or not X is a subspace. And so in problem 1.1, X is equal to the set of all vectors X, Y, Z in V such that Y is equal to 0. Now, you may have a very good feeling for what the answer to this is, but try to work through it and make sure you can turn the crank and see what's going on. But anyway, 1.1 then you need to ask or you need to answer the question of whether or not that's a subspace. And then in 1.2, X is the set of all vectors X, Y, Z in V such that the X component is greater than or equal to 0, and tell whether or not that is vector space. You don't subspace. You don't need to give any reasoning or anything, although I certainly hope that you will understand the reasoning. But all you have to do is to answer the question. And then in the class period, what will be done is I will give you one more question. I'll give you 1.3. And so what you should do is go ahead and answer these two questions, because these questions will not, only the answers will be given on the test sheet that I give you in the next class period. And for this one, of course, the question will be given as well, because you don't know the question yet. So you'll have 3 things to fill out in the next period. So go ahead, but I would advise you to go ahead and do these 2 problems ahead of time and keep in your notes or somewhere else what the answers are, and then you'll work this problem in class. So I hope that, again, this is not too tedious for anyone, and we will continue our discussion of some introductory ideas in linear algebra in lecture 2. And that concludes lecture 1.